This podcast was created by Dr. Alyssa R. Jones for PSYC 5300 graduate level behavioral statistics using Notebook LM. The system was given specific parameters and restricted to content drawn from the assigned Crump Lab texts, answering questions with data and reproducible statistics for psychologists with R. The narration is produced using AI-generated voices. These voices do not represent recordings of Dr. Jones or the authors of the assigned materials. Although the podcast was generated from the designated course text, AI-produced summaries, explanations, and narration may still contain errors, omissions, or oversimplifications. Students should use each episode as a learning supplement and consult the assigned readings, course materials, and instructor guidance when clarification is needed.
Imagine publishing a breakthrough psychology paper. You've spent months running participants.
Oh, yeah, agonizing over every little detail of your experimental design.
Exactly. Cleaning your data, writing it up. You finally send it off to a top-tier journal, and then you get a reply. A peer reviewer decided to plot your raw data on a scatter plot and realizes your data points literally form the shape of a T-Rex.
A literal dinosaur.
And the crazy thing is, your summary statistics were completely perfect.
Right.
Your variance, your correlation, they all looked like a standard publishable data set. But the actual data was just a joke.
It sounds like an urban legend, but it is actually one of the most sobering realities in data science, and in psychological research especially.
Yeah.
You can have mathematically flawless, descriptive statistics that completely and utterly lie to your face. They just hide the underlying reality of the human behavior you're trying to study.
And that is exactly where we are starting today's deep dive. Welcome in, everyone. I'm your host, and joining me is our resident data expert.
Hi, everyone. Really glad to be here for this one.
Today, we are drawing heavily on Matthew J.C. Crump's materials on describing data and reproducible statistics with R. And this deep dive is specifically tailored for those of you in graduate psychology programs.
Right. The folks who are making that really scary transition from just consuming statistics in textbooks to actually actively producing them.
It's a huge leap. So we are completely skipping the basic formulas today. You already know how to calculate a mean or a median. Our mission today is parsing the implications of those statistics.
The why and the when.
Exactly. And importantly, how you handle these concepts conceptually within the R and tidyverse ecosystem.
Because, Crump's materials approach this from a very pragmatic, researcher-first perspective. Statistics in psychology, it isn't about proving some abstract mathematical theorem.
Right.
It's about answering theoretical questions with messy, noisy, chaotic human data. And human brains just cannot intuitively hold like a matrix of 5,000 individual reaction times in working memory.
No, of course not.
You can't just extract a narrative from that. So we rely on compression. We have to summarize. But, and this is the crucial part, every single time you compress data, you lose information.
Yeah, the entire art of descriptive statistics is really just choosing what information you're willing to lose, right? Yeah. And what information is too critical to sacrifice.
That is exactly it.
So I want to focus on that transition from the raw data to the summary, because it's a moment of sheer panic for a lot of first-year grad students. I remember this vividly.
Oh, the spreadsheet panic.
Yes. You export your data from Qualtrics or ePrime or whatever.
Yeah.
You load it into RStudio. You type view my data, and you are staring at an endless wall of numbers.
Just rows and rows of continuous variables.
Right. Maybe it's 500 rows of continuous happiness ratings or a massive global economic data set like the Gapminder data.
It's cognitively overwhelming.
It really is.
So your immediate instinct, just to make the anxiety stop, honestly, is to immediately run a summarize function. Give me the mean happiness score, just so you can get one single number that you can actually understand. Which, that is a completely understandable human instinct. But it is simultaneously the most dangerous thing you can do as a researcher.
Flying blind.
Exactly. Running blind calculations is exactly how you end up publishing the datasaurus. Crump's text emphasizes what he calls the look first rule.
Look first.
Yeah. Before you type mean or standard deviation into your console, you absolutely have to look at the shape of the data. And in the R ecosystem, that means your very first instinct shouldn't be dplyr.
Right, it shouldn't be the data manipulation.
No, it should be ggplot2. You have to visualize it.
So let's talk about ggplot2 and that initial visualization phase. Because if you just take those 500 happiness scores from the source material, which range from -infinity to +infinity, totally unconstrained, and you just plot them as a single dot plot on a single axis.
You just get a thick black line of ink.
Exactly. Or if you spread them out by participant ID, you get what looks like a swarm of angry bees.
Yeah, a total mess.
You haven't summarized anything yet. You've just changed the medium from a spreadsheet to a graphic.
Right, because a raw dot plot of thousands of data points usually suffers from overplotting. The dots literally just sit on top of each other. You still can't extract the narrative.
So what's the fix?
This is where the histogram becomes your primary diagnostic tool. A histogram forces structure onto the chaos by grouping continuous numbers into discrete bins.
Okay, bins.
Yeah, you are essentially telling R, hey, don't show me every individual person. Show me how many people fall into the specific neighborhood of scores.
I always think of it like taking a massive jar of loose change that you've saved up for a year. If you dump it on the floor, that's your dot plot.
Just a chaotic mess of copper and silver.
Exactly. You can't tell how much money you have. But if you start sorting them into a stack of pennies, a stack of nickels, a stack of dimes suddenly, you can assess your wealth at a single glance.
That's a great analogy.
Right. The height of the penny stack tells you the frequency of that specific value. In R, those stacks are your bins. And plotting that with histogram immediately reveals the structural reality of your data.
But here is the critical methodological choice you have to make as a researcher. And it's something R will actually try to do for you by default, which, frankly, you should always override.
Oh, the default bin width.
Yes. R will pick a default bin width, but choosing that width is what we call a Goldilocks problem.
Too hot, too cold.
Exactly. If you set the bin width argument too wide, say, you group happiness scores in huge chunks of 2,000 points, you overcompress the data.
You might end up with just two massive blocks on your screen.
Right, you've smoothed away all the nuance. You might be hiding a bimodal distribution where you actually have two very different, distinct subgroups in your sample.
Which would completely change how you interpret the psychology of the phenomenon. I mean, if you have a bimodal distribution, reporting a single average is essentially reporting a number that represents nobody in your actual study.
Exactly. It's the average of two extremes, which is just empty space. And then on the flip side, if you set the bin width too narrow, say, bins of just 2 points, your histogram looks like a jagged, broken comb.
Because it's picking up on every little bit of noise.
Right. A bin width that is too narrow fails to compress that random sampling error. You end up visualizing the noise rather than the true underlying population distribution.
Like, maybe nobody in your sample happened to score exactly between 412 and 414 milliseconds, so you have a gap in your graph.
Yeah, but that gap doesn't mean it's psychologically impossible to have that score. It's just noise. So as a researcher, you really have to iterate. You change the bin width in your ggplot code, you rerun it, and you visually inspect it until the underlying shape stabilizes.
Okay, so we've iterated. We have a solid histogram. We can actually see the shape of the data. And usually we're hoping for that nice symmetrical bell curve. But, in psychological research, we rarely get that lucky.
Almost never.
Right. So once we understand the shape, we have to start translating that visual shape into numerical summaries for our manuscript. Because you can't just put 50 histograms in the results section of a paper.
Reviewers tend to hate that.
Yeah, they really do. So we need to measure what the text calls sameness, central tendency, the gravitational center of the data.
Right. When a colleague asks you, hey, what is your data like? They are asking for the central tendency. They want to know the typical experience of a participant in your study.
And as graduate students know, we have 3 primary tools for this, right? The mode, the median, and the mean. And the text really focuses on the conceptual utility of each, rather than just the basic arithmetic.
Which is so refreshing.
Let's just bypass the mode quickly, because for continuous psychological data, it's often practically useless.
Totally.
Like if you are measuring reaction times down to the millisecond, every single participant might have a completely unique score.
Yeah, the mode might technically be the one arbitrary millisecond that 2 random people happen to share.
Which tells you absolutely nothing about the broader data set.
Yeah.
So the real debate in a lab meeting almost always comes down to the mean versus the median.
And that debate hinges entirely on the shape of the distribution you just plotted in your histogram. We all understand the basic mean arithmetic. You sum the scores, you divide by n. But Crump's material asks us to conceptualize the mean differently.
How so?
It asks us to see the mean as a physical balancing point. It is the one specific value that, if you replaced every single raw data point with this new value, the total sum of the data set would remain perfectly unchanged.
It's the great equalizer. I always think of it as Robin Hood.
Robin Hood.
Yeah. If you took all the wealth, or in our case, all the happiness points or all the milliseconds of processing time, and you put it into a giant communal pool and then redistributed it perfectly equally to every single participant, that equal slice is the mean.
I see.
It forces perfect equality on the data.
That is actually a highly functional way to conceptualize it. But the problem with Robin Hood is that he is blind to extreme wealth disparities, mathematically speaking.
Right.
And this is exactly where graduate students often get trapped by their own data. The mean cares deeply about every single value in the data set. Because it pools everything together, an extreme outlier contributes a massive amount of weight to that total pool.
Yes. Here is a dynamic I saw in my cohort constantly. We'd be running a cognitive task, maybe like a Stroop task. Most reaction times are hovering around, say, 400 to 600 milliseconds.
Pretty standard.
Yeah. But then you look at the raw data, and participant 12 has a single trial that took 8,500 milliseconds.
Oh, wow.
Clearly they sneezed or their phone buzzed or they just completely zoned out.
Yeah.
And our immediate instinct was always, well, we have to delete that trial because it's going to completely ruin the mean.
Right.
But deleting data feels inherently dirty. It feels like manipulation.
Right. And depending on how you document it, it absolutely can be. The philosophical question you really have to ask yourself is, what are you trying to measure? Are you trying to measure the average of everything that literally happened in the room, including the sneezes and the phone buzzes? Or are you trying to measure the typical underlying cognitive processing speed?
Definitely the latter, usually.
Right. So if it's the latter, the mean is simply the wrong tool for a data set with extreme positive skew.
Because reaction time data is practically never normally distributed, there's a biological floor. You cannot physically perceive a stimulus and press a button in 10 milliseconds.
Right. Physics just won't allow it.
So the data is strictly bounded on the left. But on the right side of the distribution, there is no boundary. You could theoretically sit there for an hour before pressing the button. So RT distributions always have this long trailing tail to the right.
Precisely. It is a classic positively skewed distribution. And when you calculate a mean on positively skewed data, the extreme values in that long right tail, the 8,500 millisecond, sneezes violently pull that balancing point toward them.
Because they're adding so much to the Robin Hood pool.
Exactly. The mean gets artificially inflated. It tells you the typical reaction time is much, much slower than what the vast majority of your participants actually experienced.
Which brings us to the hero of skewed data, the median. If you use the median, you don't actually have to manually delete the 8,500 millisecond outlier.
Nope.
You don't have to justify some subjective data trimming procedure to reviewer 2.
Because the median simply does not care about the magnitude of the extreme values.
Right.
The median just requires sorting the data from lowest to highest and locating the exact physical center of the line. It counts positions, not weights.
Ah, positions.
Yeah, whether that maximum value at the end of the line is 800 milliseconds or 8,000 milliseconds, it still only occupies one single position at the end. The median calmly stays right in the dense center of the data.
The source material grounds this in a non-psychology example that I think illustrates the real-world stakes of this mathematical choice so beautifully. It references using the Gapminder dataset in R, looking at GDP per capita across different continents.
Such a great data set to play with.
It is. And economic data behaves exactly like reaction time data. It is bounded at 0. I mean, you can't really make less than $0, but it has an infinite right tail because billionaires exist.
Right. Economic data is the quintessential log-normal distribution. If a researcher or, say, a policymaker wants to summarize the income of a specific region and they choose to report the mean GDP per capita, they're essentially committing statistical malpractice if their goal is to communicate the typical lived experience of a citizen.
Exactly. Let's say you run your dplyr code, right? You group by country, you summarize the average income using the mean. You might get an output saying the average income in a country is $75,000.
That's pretty good.
Sounds great. But if you were to actually walk down the street and ask people, almost nobody makes $75,000. Most people make $35,000. But the country happens to have 50 multi-billionaires.
And there's the Robin Hood problem again.
Yes. Those 50 billionaires dump so much extreme wealth into the communal pool that the perfectly redistributed mean income looks artificially fantastic.
And, a politician might love that mean because it inflates the perceived prosperity of the region. But as a scientist, your job is accurate representation.
Right.
By simply swapping the mean function for the median function inside your dplyr summarize code, you report the exact middle income. The income where exactly 50% of the country makes more and 50% makes less.
Which is highly robust to the billionaires.
Completely robust. It tells the true story of the central tendency.
So the takeaway for grad students building their R scripts: do not blindly type mean. Ask yourself, what is the shape of my data? If it's perfectly symmetrical, sure, mean and median will be identical.
Yeah, it won't matter.
But if it is skewed, which it almost certainly is if you are dealing with reaction times or income or really any variable with a hard biological or physical floor, you need to carefully justify why you're reporting a mean instead of a median.
And I mean, it's worth noting that in cognitive psychology, there are advanced techniques beyond just picking the median.
Like what?
Like fitting ex-Gaussian distributions to RT data to actually analyze that long tail separately from the normal component.
Oh, that's fascinating.
It is, but at the foundational descriptive level, just understanding the fragility of the mean is paramount.
Okay, so we've mastered sameness. We can find the center of gravity in our data, but that leaves us with a gaping hole in our understanding of the data set.
A massive hole.
Because if I tell you two different experimental groups both have a mean happiness score of 5, you actually know almost nothing about how those two groups behaved.
You know absolutely nothing about their differentness. Central tendency is really only half of the descriptive equation.
Right.
The complementary question is variability.
Yeah.
How spread out are the scores around that central balancing point?
Because Group A could consist entirely of people who rated their happiness as a perfect 5.
Yeah.
No variation at all. A completely homogeneous sample.
Everyone is just right down the middle.
Exactly. But Group B could consist of half the people rating a 0 absolute misery and half the people rating a 10 euphoric bliss.
Wow, yeah.
The mean for both groups is exactly 5. But psychologically, Group A is stable and neutral, while Group B is severely polarized. If you only report the mean in your paper, you are hiding the most interesting part of the psychology.
Which brings us to the actual mechanics of how we quantify that differentness. And the source text walks through this logic in a way that I think finally demystifies a lot of the anxiety around variance formulas.
It really does.
Because if we want to know the average amount that scores deviate from the mean, the most intuitive human logic would be find the mean, subtract the mean from every single raw score to see how far away it is, and then just average those different scores.
Right. It makes perfect intuitive sense. Let's say the mean is 10. A score of 12 has a difference of +2. A score of 7 has a difference of -3. You just figure out all those distances, you add them up, and divide by the total number of scores.
Simple, right?
Very simple. But there is a fatal trap here.
The sum to zero trap.
Yes, the sum to zero trap. It's mathematically inevitable. Because the mean is the exact physical balancing point of the data set, the amount of positive weight above the mean will always, perfectly, 100% of the time, equal the amount of negative weight below the mean.
By definition.
Right.
The mean is explicitly calculated to be the exact center of the values. Therefore, if you sum the raw deviations from the mean, the positive deviations and negative deviations cancel each other out entirely.
Every single time.
The sum will always be exactly 0. And if you try to find the average deviation this way, 0 divided by n is just 0. The math literally tells you there is 0 variability, even when you can plainly see with your own eyes that the scores are spread out.
So we have an engineering problem.
Mm-hmm.
The negative signs are destroying our ability to measure distance.
Mm-hmm.
Now, when I was first learning this, I had a very specific pushback in my head.
What was that?
I thought, well, distance is distance, right? Like if I drive 5 miles north or 5 miles south, my car still puts 5 miles on the odometer. It doesn't subtract 5 miles.
Right.
So why don't we just strip the negative signs away? Just take the absolute value of every different score, add those positive numbers up, and find the average.
I mean, it's an incredibly astute observation, and it's actually a very real statistical measure called the mean absolute deviation, or MAD.
Oh, really?
Yeah, the text validates this exact intuition. Using absolute deviations completely solves the zero-sum problem. It tells you exactly the average physical distance scores fall from the mean. It is highly intuitive.
Okay, so if it's so intuitive and it completely solves the problem, why did I have to spend my entire first year of grad school wrestling with the sum of squares? Why is squaring the deviations the universally accepted standard in psychology instead of just dropping the negative sign?
It ultimately comes down to the downstream mathematical properties required for inferential statistics.
Okay.
Historically, statisticians realized that absolute values create sharp corners in mathematical functions. Like in calculus, you can't easily find the derivative of an absolute value function at zero. It's not a smooth curve.
The math breaks down later on.
Exactly. But if you square a number to get rid of the negative sign, because, a negative times a negative is a positive, you create a smooth parabolic curve. And that smoothness is strictly necessary for the advanced probability math that underlies ANOVA, regression, and essentially all the inferential models we use in R today.
Okay, so we basically sacrifice a little bit of intuitive simplicity early on for the sake of higher order calculus downstream.
That's a good way to put it.
I can accept that. So we take every different score and we square it. -3 squared becomes +9, +2 squared becomes +4. Then we add all those squared numbers up.
And that is the infamous sum of squares, or SS.
Which haunted my nightmares.
Right. But if you can understand that SS simply means the total piled up amount of squared differentness in my data, a massive amount of statistical jargon suddenly becomes transparent, like analysis of variance, ANOVA. You are quite literally analyzing the sum of squares.
It all connects. So to get the average differentness, we take that sum of squares and divide it by the number of observations, or technically n-1 for a sample, to correct for bias. There's a whole rabbit hole for another day.
Definitely another day.
But that division step gives us the variance.
Yes. Variance is the average of the squared deviations. But as the source material is quick to point out, variance is conceptually terrible to look at as a descriptive statistic.
It really is.
It is mathematically vital, but descriptively, it's pretty much useless.
Because it is entirely divorced from the original scale of your data. Think about it. If you are measuring reaction times in milliseconds, you find the deviations, and then you square them. So your variance is reported in squared milliseconds.
Right.
What on earth is a squared millisecond? How do you conceptualize that psychologically?
You can't. You just can't. If you are measuring height in inches, your variance is in squared inches, which is an area, not a length. Because squaring inflated the numbers exponentially to get rid of the negative signs, the variance is a massive, uninterpretable number.
Right. If your mean happiness score is 5 on a 10-point scale, your variance might be something like 16. It doesn't map onto the reality of the questionnaire at all.
So we need a janitor.
A janitor.
Yeah, we made a huge mess by squaring everything just to solve the negative sign problem, and now we need to clean it up before we publish the paper. If the problem is that the numbers are squared, the solution is the exact inverse.
We simply take the square root of the variance.
Exactly, and that gives us the standard deviation.
It is so deeply satisfying to trace that lineage. The standard deviation isn't just an arbitrary formula sent down from statistical heaven. It is a highly engineered, practical hack.
It really is a hack.
It shrinks the variance back down to the original natural units of your data. If your variance was 16 squared points, your standard deviation is just 4 points.
And now you have a highly communicative, descriptive package. You can write in your manuscript, the mean happiness score was 5, with the standard deviation of 4.
Which makes sense to a human reader.
Right. You are telling the reader the exact balancing point of my data is 5, and the typical participant deviated from that center by roughly 4 points in either direction. With just 2 numbers, you have completely reconstructed the shape and spread of the entire distribution in the reader's mind.
Okay, so we have our tidyverse workflow. We can group our data, we can calculate the mean, we can calculate the standard deviation. We output a beautiful, clean table. Are we safe? Can we just copy that table into our manuscript and call it a day?
If you stop at the numerical summaries, you are walking into a trap.
Oh.
And this is perhaps the most vital warning in the entire source text. We have built these beautiful summary statistics, but we must never forget that they are compressions. They are lossy.
Like saving a JPEG too many times.
Exactly like that. And sometimes the information that gets lost in the compression is the entire fundamental truth of the data set.
This brings us back to the nightmare scenario I mentioned in the hook. I really want to talk about Anscombe's quartet because it completely shatters the illusion that summary statistics are sufficient on their own.
Frank Anscombe was a statistician in the 1970s, and he was deeply concerned about researchers becoming too reliant on computation, especially as computers were becoming more common in labs. He wanted to prove that numbers alone could blind you to the reality of the data.
Okay.
So he mathematically engineered 4 distinct data sets. Each data set just has pairs of X and Y values.
And when you say distinct, you mean they aren't just slightly different? The relationships between X and Y in these 4 data sets are fundamentally categorically different stories.
Very different. If you actually plot the dots on a graph, dataset 1 is a classic, messy, linear scatter plot. Just a standard positive correlation scattered around a
It's a
line.
standard psychology data.
Right. Dataset 2 is a perfect, smooth parabola, a highly deterministic, U-shaped curved relationship. Dataset 3 is a perfectly straight line, but with one single massive outlier located far away from the line.
Okay.
And dataset 4 is just a vertical stack of dots where x doesn't change at all, driven entirely by one extreme outlier pulling the correlation.
So the underlying psychology or, the mechanism generating those 4 data sets would have to be completely different. You would theorize completely different mechanisms for a linear relationship versus a U-shaped curved relationship.
Absolutely. And this is Anscombe's brilliant trap, if you feed those 4 datasets into R and you summarize to calculate the descriptive statistics,
Robin.
the mean of x is exactly 9.0 in all 4 datasets. The variance of x is exactly 11.0 in all 4. The mean of y is 7.5 in all 4. The variance of y is 4.12 in all 4. And the Pearson correlation between x and y is exactly 0.816 in all 4.
Wow. Every single standard descriptive and inferential summary statistic is identical to the decimal point.
To the decimal point.
If a grad student just ran the numbers, looked at the output table, and didn't plot the data, they would confidently assert that these 4 datasets are identical.
They absolutely would.
They would publish a paper claiming a linear relationship for dataset 2, when in reality it's a perfect curve. They would completely misinterpret the phenomenon.
It is a devastating critique of blind computation. Anscombe proved mathematically that summary statistics can hold the exact same values for infinitely different structural geometries.
And researchers have taken this concept even further with modern computing, right?
Yeah.
The source text brings up the data source dozen, which was created by researchers at Autodesk.
Yeah.
They took Anscombe's idea of constraint-based dataset generation and they pushed it to the absolute limit.
Yeah, using simulated annealing algorithms, they created a dozen data sets that share the exact same mean, the exact same standard deviation, and the exact same correlation as a standard messy scatter plot. But when you map the x and y coordinates,
One data set forms a perfect 5-pointed star.
Yep.
One forms a circle, one forms intersecting lines, and yes, the famous one literally forms the outline of a Tyrannosaurus Rex.
it's hilarious to look at, but I mean, it sends a chill down your spine as a data analyst.
It really does. Because if you don't use dplot2 before you use dplyr, your data could literally be a dinosaur, and your summary statistics will smile and lie to you,
Yeah.
telling you everything is perfectly normal.
This is exactly why the tidyverse ecosystem in R is designed the way it is. It is designed to tightly integrate data manipulation with visualization. You shouldn't just be generating tables, you should be piping your summaries directly into visual geometries.
So let's walk through what that unified workflow actually looks like conceptually for a psychology grad student. Because the tidyverse is built on a very specific philosophy, the pipe operator.
Ah, the pipe.
In base R, you have to nest functions inside of functions inside of functions. It reads from the inside out like a complicated math equation, the parenthesis, subset parenthesis, data, comma, condition equals A. It's hard to read, and it's super prone to error.
Hadley Wickham and the tidyverse team fundamentally changed how we interact with data by turning coding into a linear grammar. The pipe operator literally translates to and then.
And then?
Yeah, you start with your raw data, and then you group it, and then you summarize it. It treats data analysis like a conveyor belt in a factory.
So let's run a hypothetical cognitive psych experiment through this conveyor belt. We have our raw data, right? Let's call it my data.
Right.
We pipe it. First, we need to organize the chaos. We use group by condition.
Group by is a fascinating function because it doesn't actually change the data you see on the screen. It changes the metadata under the hood. It secretly tags every row. It tells R, hey, from now on, do not treat this as one giant pool of participants. Treat this as 2 completely isolated buckets, the control group and the experimental group.
It's the coin sorting step. We've separated the nickels and the dimes. Now we pipe it again. And then summarize. Inside the summarize function, we define the new variables we want to create.
Right.
So, RT equals mean reaction time. And because we know we need the differentness, we add SDRT equals SD reaction time.
And because of that group by step, earlier on the conveyor belt, summarize knows to apply those formulas independently to the 2 buckets.
Right.
So instead of returning a 10,000 row data frame, the conveyor belt spits out a pristine 2-row data frame. Row 1, control, mean is 400, SD is 50. Row 2, experimental, mean is 600, SD is 120.
It is incredibly elegant. But as Anscombe and the Datasaurus taught us, we can't stop at the table. The final step of the conveyor belt has to be visualization.
Always.
You can actually pipe that summarized data frame directly into ggplot2.
We build a bar chart. The height of the bar visually communicates the sameness. The reader can instantly see that the experimental group was, on average, slower than the control group.
But a naked bar chart is a statistical sin.
It really is.
It implies absolute certainty. It hides all the variability we just calculated. So we add a layer, and this is where the tidyverse really shines. We add GM error bar, and we tell it to use the standard deviation we just calculated to determine the height of those error bars.
The error bars visually communicate the differentness. You draw a line extending one standard deviation above the mean and one standard deviation below.
Brilliant.
At a single glance, a reader looking at your published paper gets both halves of the coin. The bar height is the central tendency. The error bar spread is the variability.
And it tells a crucial story. If the experimental group has a massive error bar, say, an SD of 120, while the control group has a tiny error bar, an SD of 10, the experimental manipulation didn't just slow people down on average.
Right.
It introduced massive instability into their performance. Some people were unaffected, while others were completely derailed. The variance itself becomes a psychological finding.
Exactly. Variability is so often treated as just a nuisance, as noise we just want to get rid of so we can find the true mean effect.
Yeah.
But in psychology, the variance is often where the actual individual differences live. Why did a treatment work for half the group and fail for the other half? The mean hides that failure. The variance highlights it.
This has been a really profound journey into the underlying mechanics of how we describe reality with numbers. We started with the cognitive overwhelm of a raw spreadsheet, and we learned why the absolute first step must always be to plot the data.
See the shape before the math blinds you?
Exactly. We pulled apart the concepts of sameness and differentness. We saw how a positively skewed distribution, like reaction times or economic data, can violently inflate the mean, making it a dangerous tool for summarizing typical experience.
And we explored why the median often serves as the more robust, honest alternative when those outliers are present.
We dug into the engineering of the standard deviation. We solved the sum to zero trap by squaring the deviations, recognized the resulting variance as conceptually uninterpretable, and used the square root to bring our summary back down to the natural readable scale of human experience.
And of course, we internalized the ultimate warning of the Datasaurus. Summary statistics are compressions, and compression is inherently lossy.
We learned how the tidyverse workflow group, by Summarize and Gplot, synthesizes computation and visualization into a seamless, reproducible process that protects us from those blind spots.
It really is an essential toolkit.
But before we close out, I want to leave you with one final, lingering concept drawn from the very end of Crump's material. It's a concept that completely shifted how I view statistics. The text briefly mentions the idea of rolling your own statistics.
Which is a radical thought for a lot of students who are taught that statistics is this rigid rule book handed down by history.
Right. We spend so much time memorizing that you must calculate variance by squaring the different scores, raising them to the power of 2. It's the default setting in R. It's the default in SPSS.
It's everywhere.
But mathematically, if the only goal is to solve the negative sign problem, there are an infinite number of even numbers. You take all the different scores and raise them to the power of 4, or the power of 6, or 8.
Mathematically, that is entirely valid, but it would fundamentally change the philosophical nature of the statistic.
How so?
Well, if you square a deviation of 10, it becomes 100. If you raise that same deviation to the 4th power, it becomes 10,000.
Oh, wow. It exponentially penalizes outliers. It would create a measure of variability that is hypersensitive to extreme deviations, far more sensitive than standard variance.
Which might be exactly what you want if you are, say, an aerospace engineer where an extreme deviation means a plane crashes. You want a statistic that screams at you when an outlier exists.
But what if you are a psychologist? Here is the provocative thought for you to mull over the next time you open up our studio and automatically type standard deviation.
Mm-hmm.
The tools we use, the mean, the standard deviation, they are not objective facts of nature.
No, they're not.
They are human inventions, engineered with specific mathematical trade-offs, mostly developed a century ago for agriculture and genetics.
We just use them because they are standard conventions, but they are just one specific lens through which to compress reality.
So what unseen, undiscovered, descriptive statistic might perfectly capture the weird, specific nuances of the human mind in your specific data set?
It's a great question.
If we stopped blindly accepting the default functions, Could we design a new central tendency or a new variability measure uniquely tailored to the shape of psychological data? Are we limiting our theoretical understanding of human behavior simply because we're using the default math?
It challenges the researcher to take ownership of the computation. You are not just a technician running code, you are the architect of how that data is compressed and communicated to the world.
Keep questioning the defaults, keep plotting your raw data, and until next time, keep diving deep.